All right, so today we're going to talk about the electromagnetic spectrum of light. So electromagnetic just means light, and not just light that you can see with your eyes, but the light that you can't see either. So that means radio waves, gamma rays, ultraviolet, infrared, all that. Okay, and we're going to I'll start right here. Well, we'll start here on the end, and we'll start looking at sort of the anatomy of the spectrum. So this right here on the left end here are long wavelengths. So that whether it's visible light or radio waves or whatever, these wavelengths are really long. And as we go to the right, the wavelengths get smaller and smaller and smaller, all the way down to this end where we have, okay, so these are the short wavelengths. This is the long wavelength end of the spectrum. And by long wavelengths, I mean that some of the wavelengths on the end of the spectrum can be kilometers long. Like this is radio waves down here. And down on the short wavelength, they can be billions of meters long. All right, so it's a spectrum because it's continuous. It starts really long wavelengths and ends up with really, really short wavelengths. I think the best place to start is we'll just start right in the middle. And this would be the visible part of the spectrum. So this is the part of the spectrum that your eyes are sensitive to. And you know what's in here. Remember, these are the long wavelengths, it's shorter wavelengths. So down here on the longest wavelength part of the visible spectrum, we have red light. And then a little bit shorter wavelength, orange light, yellow, green, blue, and violet light. So the important part of this is that red is a longer wavelength than orange, which is longer than yellow, green, blue, violet, and by length, the red end, this is around 700 nanometers. That means red light, its wavelength from crest to crest is around 700 millionths of a meter. And they get smaller and smaller and smaller. You get down to violet, and it's around 450 nanometers. So red is longer, not particularly long wavelengths, millions of meters, but it's still longer than orange and all the way down to violet. Okay, and you are sensitive to this because your eyeballs, when this particular section of the EM spectrum between 700 and 450 nanometers, when those wavelengths enter your eye, they go to the back of your eye where there are a bunch of rods and cones, little sensors that pick up, that absorb these wavelengths of light and send a signal off to your brain. And your brain interprets them into images. Okay, so we need to talk about not only wavelength though, because these are long wavelengths to short wavelengths. We need to talk about the speed of the waves and the frequency of the waves. There's one overarching equation it's called the light equation for the EM spectrum, is the speed of light is equal to the wavelength times the frequency. And the speed of light is 300 million meters per second. And we're talking about a little bundle of energy that we call a photon that travels at 300 million meters per second. That equates to about 186,000 miles per second. That's pretty fast, and that's the speed limit for the universe. Nothing goes faster than light. But the speed of light, c, is a constant. So light travels 300 million meters per second, period. That never changes. But you'll note, we start at the long wavelength end, and the wavelengths get smaller and smaller. So if we're talking about starting on the left and the wavelengths get smaller, because this is a constant, if the wavelength is getting smaller, that means the frequency must be getting higher. Remember, this is just a measure of how long the waves are. The frequency is how many waves are passing by in a second. So we have meters per second. Okay? And now so here we have visible light. We'll go to the section that is just longer wavelength and higher frequency, lower frequency, longer wavelength, lower frequency. And that is, okay, this is red. This is infrared. Okay, so that is a lower frequency than red. And that's just heat. You might know it better as heat. If you stand in front of a campfire, you feel the infrared radiation coming off of it. If you stand outside on a sunny day, you feel the heat from the sun. You feel that infrared radiation. Okay? And it's no different than visible light in that it's still a photon traveling at 300 million meters per second. The only difference between the light that your eyes are sensitive to and the light that, well, every bit of you is sensitive to, heat, is the wavelength and frequency. It's the same thing traveling at the same speed, just has a different wavelength and frequency. And obviously this is used for heat lamps or heaters of all kinds. Okay. And here let's move to the section of the spectrum that is higher frequency than violet. Okay, so this is ultraviolet. Okay. And you're also sensitive to this, but your eyes aren't sensitive. You can't see ultraviolet, but you can certainly, your DNA senses it. You know that tanning beds, there's a couple of ranges. They have UVA and UVB. Well, here, and hopefully you also know that getting too much sun is not good for you, and it's not because of all the visible light or of all the heat. It's because of the ultraviolet. And the way ultraviolet is bad for you is, you have your DNA change in your cells. It turns out that some of these ultraviolet rays, they match the energies in your DNA chain, and your DNA chains absorb it, vibrate, and your DNA can be broken. Okay, so ultraviolet light can cause your DNA chains to break. And if the cell dies, if a DNA chain in the cell was broken and the cell died, that cell would be replaced by a healthy one. But if the cell survives the damage, that's not good for you. Now you have a damaged cell with bad DNA that can replicate itself and can cause cancer. But ultraviolet is used, well, obviously for tanning, and it's also used for sanitizing, I can't spell, sanitizing things like in a laboratory or a hospital. They use ultraviolet light to sanitize. All sorts of different uses for it. And I think we'll keep on working to the shorter wavelengths, higher frequency down here. So even a higher frequency than ultraviolet are X-rays. And you know what those are used for. They're all sorts of medical uses. Okay? But we're just got to keep in mind that there is nothing different about an X-ray, an ultraviolet ray, a visible ray, an infrared ray. There's nothing different. They are all a photon, a bundle of energy that was created by electrons vibrating in atoms in the sun or a light bulb or whatever, traveling at 300 million meters per second. The only difference between the light that your eyes are sensitive to and X-rays is their wavelength. The X-rays have a much shorter wavelength, but they have all sorts of different uses. They're, you've probably had an X-ray, and the same thing occurs that X-rays are damaging to your DNA. They can hurt your DNA. That's why when you go get an X-ray, if they're X-raying your arm, they cover up the rest of you because they don't want you getting any more X-rays than you need to get to create the X-ray. And that's also why the X-ray technician leaves the room before they give you the X-ray, because they don't want to be in there. They don't want to absorb any more X-rays than they have to. Okay, so we have relatively long wavelength infrared, shorter wavelength visible, ultraviolet, X-rays, and down here the highest frequency, shortest wavelength are gamma rays. And these also have a medical use. They can use them they'll also damage your DNA. but they'll also damage the DNA of cancer cells. So they can use gamma rays for radiation therapy. If you have something like cancer, they can use it to kill cancer cells. Okay, and now that we're down at the end here, this is the short wavelength, high frequency. This is the low frequency end. Okay. This is also the high energy end of the spectrum. Gamma rays have much more energy. It's the same photon traveling at the same speed. They just have really short wavelengths and a lot more energy. And this down here is the low energy end of the spectrum. Okay, so we have really high energy gamma, and as the wavelengths get larger, we have X-rays, ultraviolet rays, visible light, infrared. We're going to break the last bit of it up into two. This is the radar section. So these are much longer wavelengths. These are on the order, radar is on the order of meters, like 1, 2, 3 meter wavelength. And there's one very specific frequency. You probably have one of these in your kitchen. Microwaves have a frequency of 2,450,000,000 hertz. So microwaves make little waves of energy by making 2,450,000,000 vibrations per second. And that equates to a wavelength of 0.12 meters. And it turns out this was discovered, microwave ovens were discovered and created during and just after World War II, because a radar technician noticed that the chocolate bar that he had in his pocket, he brought with him every day, melted when he was working at this particular frequency and wavelength. And that's because some fat, but mostly water molecules, this one specific frequency matches the bond energy in water between the oxygen and hydrogen, causes the oxygen and hydrogen it absorbs the energy, they start to vibrate, and all those water molecules or fat molecules in your food vibrate and move next to each other, and by friction they heat up, create a lot of heat, and heat your food. So microwaves heat your food with friction as long as there is water or some fat in it, certain fat molecules. Okay, and this is also obviously used for aircraft. I don't think I can draw an aircraft. Okay. They send out a radar signal, it bounces off the plane and comes back to the detector, and they know where the plane is. Okay, and you're not allowed to, other than a microwave oven, you're not allowed to have a transmitter in the radar range. People aren't allowed to just have a radar transmitter in their backyard, which would mess up air travel. Okay, and then we move on to the last one, radio signals. These are the long wavelengths. As I said before, these wavelengths can be kilometers long, but it's still a photon traveling at 300 million meters per second. It's no different for any of these. They're the same thing at the same speed, just different wavelengths and frequencies. And down here, I'm not exactly certain of the order, but at the low end of radio are Wi-Fi transmitters. So there's a section in there. So you would have something that transmits down here. And then cell phones. And then television, AM, and FM radio transmissions. So all you're talking about, the only difference in these things is their wavelength. They get longer wavelengths and shorter and lower frequencies. Still a photon, still traveling 300 million meters per second. So you're going to have a quiz over this next class, and you'll be given a blank one, just like what I started with. You'll get a blank one, and I'll want you to be able to, in order, place radio, radar, infrared, visible, ultraviolet, X-rays, and gamma rays, and know which is the long wavelength and the short wavelength and the low frequency and the high frequency, and know a way that humans use all of these, but that's okay. You know what radar and X-rays and everything are used for. So just prepare for that. Thank you.